guess it got them through the HR application sorting algorithm.
Welcome back to ECE 441A, 541A. We must have had an exam the last time we met. Everybody, or where is everybody? Anyway, today I want to remind you about lab number 1. That is due to be turned in a week from today if you haven't already submitted that to the assignment Dropbox. Homework number 3 will be forthcoming, and just so it's on your calendar or schedule, exam number 2 is on the 19th of October. Today we'll start with an exercise going from transfer functions to state space. We really haven't talked too much about that, and so I want you to start thinking about how do we go from a transfer function to a state space, and then we will discuss in general the techniques that we have developed, and we want to work then with creating or developing all of the techniques or different techniques for converting between different system representations. We will actually create one such representation. You know that the state space representation, it's not the, it's an A. It's not unique. We'll develop one of those, an input feed forward state space representation today. We'll look at an example of that for a strictly proper transfer function, and a strictly proper transfer function is when the degree of the numerator is strictly less than the degree of the denominator. Then we'll discuss how to handle a proper transfer function when the numerator degree equals the denominator degree, and essentially it's long division. So do one step of long division, and we will have then the remainder piece, the remainder term, falling into a strictly proper transfer function, with the constant being our direct feed-through term in the state space representation. That's a little bit of a precursor. What I want to do now is have you spend a little time trying to create a state space representation for the following transfer function. G of s is 4s plus 6 over s cubed plus 7s plus 12. Start trying to find a state space representation for that transfer function. And let me give you 3 minutes to at least develop your thoughts and a strategy for that, or an approach. How would you get started and how to proceed?
Are we assuming G is Y over U?
So now we're assuming that G is some output expression over some input, and we've typically said G of S is Y of S over U of S, and Y of S is the output, U of S is the input. But this is some system that has a transfer function. That could be a mechanical system, it could be an electromechanical system, it could be a filter. It's now some transfer function between an input and an output. I'm assuming everyone's finished, at least with a strategy. So what did you try? Somebody asked initially, well, is g of s really just y of s over u of s? So now we have 4s plus 6 over s cubed plus 7s plus 12. That's our g of s. Did you even know where to start or how to proceed in trying to find a state space? Or what if you didn't? What if now somebody asks this on an interview question and they say, I want a state space representation from this transfer function? What could you say? Well, one thing, to give yourself time, you might say, well, let me look at a more basic transfer function. Let me just simplify it and get started and show you sort of my thought process. This is, I'm talking to the interviewer now, and I'm saying, let me just take a simpler case to sort of show you the strategy. And so you might say, what about if I looked at the following transfer function, g2 of s, equaling 4 over 2s plus 6? Does that make you feel a little bit more comfortable? And why? Why is this one different? And why would that maybe make you feel a little bit more comfortable or confident in your strategy? What's the difference between g and g sub 2? What are some differences? Pardon? The order of the denominator, which is then the order of your system. G of s is what order? Third order. So if you're thinking about a state space representation, how many state variables are you expecting to have with G? 3. You're expecting 3 state variables, which if you're now thinking about an all-integrator block diagram, you're thinking, oh, I need 3 integrators in my block diagram. In the second one, in G sub 2 of s, what's the order of that system? First order. You're looking at 1 state variable, 1 integrator in an all-integrator block diagram. What about the numerators of those 2 transfer functions? Are they different in any way? And if they are different, obviously one's 4s plus 6 and the other one's 4. They're not equal. But what does that really mean? There's a 0. There's a finite 0 in the first one, and in the second one there isn't one. And does that impact anything? Does that change the number of integrators that we need to have in our system? And in fact, it does not. So we need to make sure that we're playing with these concepts properly. What if we take G sub, and the other thing, comparing the denominators, what's different about G sub 2 versus G sub 1 in terms of if we look at the leading power or the highest power? Okay, G sub 2 is multiplied by 2 in the denominator, the leading power, 2s. It is not monic, is it? We haven't factored out that coefficient to normalize it to 1. And that kind of messes things up. So it allows us to be more consistent if we make or force that denominator to be monic. And we could do that pretty quickly. We can say, okay, let's say now we have 4. Let me factor out the 2. And I haven't changed anything. I can now divide that 2 into the 4. And I now have 2 over s plus 3. And that's now still well, we could call it y sub 2 if you're uncomfortable with overloading the y and the u expressions, but here is y sub 2 over u. And I'm guessing now that if somebody now asks that question, is g still y over u, they were going in the following direction. Now we can cross multiply. Now we can find one equation that contains y's and u's that are now maybe multiplied by polynomials in S. If we cross multiply, we now have S plus 3 times y of S equaling 2 times u of S. Everybody comfortable with that? Now what? That's in the frequency domain, and we can now immediately take that into the time domain by remembering what S does as an operator in the frequency domain, what that corresponds to in the time domain. We know what 1 over S does as an operator. It's an integration operation. Its reciprocal or inverse is the differentiation operator. We can now put this into the time domain and say we have y prime of t plus 3y of t equaling 2u of t. Or y prime of t is equal to minus 3y of t plus 2u of t. And now can you see an all integrator block diagram that's just begging you to exist based on that first order differential equation? If you now simply had one integrator and put as an input into that y prime of t, what's the output of an integrator that has an input equaling the derivative of y? And you know this after one semester of calculus. No, maybe I guess you get this in your second semester if you get integration in your second semester. So we're really having to use quite a bit of calculus to do this. But this is now an analog computer. This is our all integrator block diagram. We have y of t, and now if we have y of t, and if somebody's giving us the input u of t, we can actually produce what y prime is equal to through a summer. We can say, oh, I can create y prime. That's just the right-hand side. That's now 2 times u of t. And it's y of t scaled by minus 3. Now I have an all integrator block diagram for g sub 2 of S, that original transfer function. And you could check that. You could take this block diagram into the frequency domain by doing what? Erasing all of the t's, capitalizing the variables, putting an s as their arguments, and doing what else? Replacing that integral with a 1 over s operator. Now you have a frequency domain block diagram, and you can use block diagram algebra, you can use Mason's gain to find the transfer function, and you better get the transfer function back that you started with. Do you see how it's kind of fun to chase your tail? Basically, you're finding the answer in the back of the book by doing that, by interrelating these different representations. What we want to do now is generalize that process. How can we expand from this g sub 2 to a process that now involves a finite zero and a higher order system? That's what today is all about. And we're going to try to find one strategy for doing that. So I cheated. I did this ahead of time. So you have to now quickly try to sketch 4 blocks. But we have different ways of writing or representing a system. We have transfer functions. We have differential equations. We have block diagrams. We have state space representations. We just illustrated how we could go from a transfer function to differential equations by cross-multiplying and going into the time domain. And we also illustrated how we could convert that first order anyway from a time domain differential equation into an all-integrator block diagram. And we can put that into frequency domain if we want as a block diagram. What we will work on next is actually now taking that block diagram and creating a state space representation from it. So here's one way. It's not a direct path from a transfer function to a state space, but we can get there through a train or a linked progression of representations. How do we go this way? Cheer. That's cheer 1, isn't it? This was you give me A, B, C, and D, and I can now give you the transfer function. And how could you go from the differential equations to a transfer function? Hit the shift key, Laplace transform. And state space, if I give you a state space, now you have all these first order derivatives. You can put those as inputs to integrator blocks, and boom, you can build a block diagram from a state space representation. And from the block diagram, you can probably read off the different relationships between those equations to get differential equations. And how do we go here? Mason's gain, or block diagram algebra. We're starting to get comfortable, I hope, with interrelating all of these different representations. And if I hand you one, if you feel more comfortable working with it in a different representation, you can quickly find that different representation. I give you a wrench, you want a hammer, so you use it like a hammer, right? So you learn how to use a hammer, you want to apply that hammer to everything. Well, we're trying to learn how to introduce more tools in our toolbox so that we're more flexible with what we can build. Now, we are starting with a transfer function. We've already gone through it for a first order, and that's between an input u and an output y. And we want to obtain a state space representation, and I already outlined the strategy. We'll go from a transfer function to differential equations. From the differential equations, we'll produce a block diagram. And once we have a block diagram, it's pretty straightforward to find a state space representation. We're simply going to label the outputs of our integrators as our state variables. If we have 20 integrators, our state space representation would be 20th order. And we would label each output as x sub 1, x sub 2, x sub 3, and then we could write the time rate of change of each of those based on what the summing junction gives you going into the input to that integrator. So let's do this for a particular parameterized form. Suppose now T of S is Y of S over U of S. Doesn't always have to be a G of S. Suppose now I have B sub 2 S squared plus B1 S plus B sub 0. And then I have S cubed plus A sub 2 S squared plus A1S plus A sub 0. And I might actually say, oh, that's really a numerator polynomial over a denominator polynomial. N of S is B2 through B sub 0. D of S is S cubed through A sub 0. And in this particular representation, I've now normalized this coefficient to be 1, and that allows our discussion to be more consistent. I've now factored out, if that was 25, I would factor it out from all of the other coefficients in the denominator, and I would divide 25 into all of the numerator coefficients. I now have a monic denominator. Now I hope that you can immediately see how we would find a differential equation relating y of t and u of t. From this, what's the order of this system? Is our transfer function proper or strictly proper, or neither? Do you remember the definition of those? Proper transfer function means the degree of the numerator equals the degree of the denominator. Strictly proper means that the denominator degree is bigger than the numerator degree. So this is actually a strictly proper, that's in the form that's easiest to work with. So now what we want to do is find or answer the following question. What is the differential equation relating y of t and u of t? We know that y of s is the transfer function times u of s, which is n of s over d of s times u of s. And now we can multiply both sides by the denominator polynomial. And we now know that d of s, y of s, is equal to n of s, u of s. Or, for this particular example, we have s cubed plus a sub 2 s squared plus a1s plus a sub 0 times y of s equaling b sub 2 s squared plus b1s plus b sub 0 times u of s. Now we can take that immediately into the time domain, because every time we multiply by s, that's like differentiating in the time domain. We now have three derivatives of of little y of t due to the s cubed y of s. We now have y triple prime of t plus a sub 2 y double prime of t plus a1 y prime of t plus a sub 0 y of t equaling b sub 2 u double prime plus b1 u prime plus b sub 0 u of t. And maybe that looks a little bit more intimidating than a first order differential equation. Now we have derivatives of y, we have derivatives of u. Now what? Well, we can start getting rid of derivatives by integrating. And what we really want to do is we want to integrate this guy, this equation, as many times as possible or as necessary so that we just end up with integrators, y's, and u's floating around. That seems to indicate that we probably need to integrate 3 times. So let's start by just integrating once and seeing what happens. If we integrate this once, y double prime turns into y triple prime turns into y double prime. And I'm actually going to keep that by itself on the left-hand side and move everything else on the right-hand side. I then have a minus a sub 2 y prime of t minus an a1 y of t minus an a sub 0 integral of y of, let's say, tau is my variable of integration, 0 to t. That's now taken care of all of my y's. And now after one integration, I have a couple of different y of t's and fewer derivatives of y. One of those y's, though, is actually inside an integral, so that will have to be pushed through an integration operation in our block diagram. Doing the same to the b's, I have plus b sub 2 u prime plus b1u plus b sub 0 integral u of tau d tau 0 to t. I can clean that up even a little bit more if the integration operation is a linear operation. I can now combine the y and the u into one, or underneath one integral, so that I now have, I can rewrite this as y double prime of t is equal to minus a sub 2 y prime minus a1 y minus, or let me say, plus b sub 2 u prime, maybe I should, well, plus b1u plus the integral from 0 to t of b sub 0 u minus a sub 0 y d tau. Are we okay with that expression? I just used the linearity property of an integration to combine so that now instead of 2 integrators, I just have 1. And the input to that integrator is going to be this linear combination, this summation of an input and an output, scaled. Let's integrate again. Since that seemed to work okay for us, we now only have a second order derivative. We can now integrate again. And I'm going to do this combining in one step. I'm going to combine the integral of u and y now together so that I now have y prime of t is equal to minus a sub 2 y of t plus b sub 2 u of t plus an integral, but now do you see what I'm going to have to do? I'm going to have to nest my integrations. That first integral that I had has to be inside the next integral. It has to be integrated twice. And I'm going to try to do this by using appropriate bracketing techniques. So let me now use a square bracket to first integrate b sub 1 u of whatever you want. Let's say it's now t tau hat minus a1 y of tau hat from 0 to t plus, and now I haven't closed up that square bracket. Am I okay to go down a line instead of continuing to scroll? I have an infinitely long wide page or an infinitely tall, but you probably only want to do the height wise. So I'm going to do a carriage return and say plus the integral from 0 to t of what I had before, b sub 0 u of tau minus a sub 0 y of tau d tau, close the square bracket, d tau hat. Are we okay with what I've done? And I don't really need to keep track of the limits on that integration. I might just get sloppy and remove those. I just need these to be integral operators. But are we okay with what I've done? I've now in square brackets incorporated a u and a y and an integral of a u and a y. So that the first u and y integrations actually are going through two integrals. And I'll have y left by itself if I integrate one more time. So now if I go one more time, integrate again, I now end up with an output that has not been differentiated. And this now is going to be an integral, and now I have to create another bracket. So let me do a curly bracket. This is b sub 2 u of tau tilde minus a sub 2 y of tau tilde plus all of my other pieces. I have the square bracket, which was b1 u of tau hat minus a1 y of tau hat plus the integral with the normal parenthesis a sub 0 u of tau minus, wake me up, b sub 0 u of tau minus a sub 0 y of tau. Close that one up with a parenthesis d tau. Close the second one up with a square bracket d tau hat. And close up the last one with a better looking curly bracket d tau tilde. And now what do we have in this? Maybe it looks messy, but it's actually quite nice because this equation only contains u's, no derivatives of u, y's, no derivatives of y. They are summed and integrated, but now we only have to have u's and y's to build this relationship. So let's now put this into an all-integrator block diagram. And the way that we will do it is we will assume that we have the output y and the input u. What is y? Well, y is the output of an integrator. So I'm going to start that on the far right-hand side and say here's y of t, and that's the output of an integrator. Do you see where that's coming from? Now, what's the input to that integrator? Well, it's inside these curly braces. And I have, let me view this sort of in a odd way, it's going to be b2u minus a2y plus the output of another integrator. So I now have a summing junction here. Maybe I didn't give myself enough vertical distance. This now is taking and subtracting an a sub 2y It's a lot easier to draw when you're sitting down and not on a tablet, and you have something a little bit more tactile than a glass screen to write on. What else does this have? It also has a scaled input, B2, and now I'm going to have my input coming along here and say there's B2. And it's also the output of an integrator. Here's U. I assume I have the input available. I have the output available, and now this has made it all the way down to the square bracket. So that now what's the input to that second or middle integral? Again, I take y and scale it by minus a1. So maybe what I should have done is, let me change this up. It'll be a little bit cleaner. I apologize. Let me call this a2 minus coming up from the bottom, and now I can do my y's like this. Is that better? Maybe, maybe not. But now I have my b's and a's stacked. The input to this integrator was a b1 times u. It was a minus a1 times y. And one more integral's output, which is the last final integral, which has an input to it as a b sub 0 scaling u and a minus a sub 0 scaling y. And now I have an all integrator block diagram that in fact is an equivalent representation of that original transfer function. Is it clear where this came from? We had a transfer function, we cross-multiplied, we took it into the time domain, we ended up with a y triple prime. We needed to integrate a few times, 3 times to be exact. We nested those integration operations, and we ended up with this block diagram, all integrator block diagram representation of our original system, T of S. Now, we're partway there, we're almost all the way there, but now we want to take this into a state space representation. And a nice way to do that is to actually label the outputs of your integrators as state variables. So let me call this output x sub 1 of t. Let me call this output x sub 2 of t. And let me call this leftmost integral's output x sub 3 of t. If x1 is the output of the rightmost integral, what's the input to the rightmost integral? The first derivative of x1. Here it's the first derivative of x sub 2. Here it's the first derivative of x sub 3. And now I actually have a strategy for writing equations for x1 prime, x2 prime, and x3 prime in terms of x1, x2, x3, and u. What is x1 prime? Do you see that it's now made up of the three signals coming into that summing junction? It's going to be minus a sub 2, and in fact, y is just x1, so we can replace y with x1 in this case. x1 prime will be minus a sub 2 x1 plus x sub 2. Now I'm working my way clockwise around the summing junction to pick up all of the arrows coming in, plus b sub 2u. That's now x1 prime. x2 prime, I don't have a tall enough screen to display, but I think you can now figure out what that is. Work our way around that summing junction again, and it's going to be x1, x3, and u. x3 prime will be x1 and u. We've run out of outputs of integrators as we work our way to the left. Let me write those down. x2 prime is now minus a1 x sub 1 of t plus x sub 3 of t plus b1 u, and x sub 3 prime is minus a sub 0 x1 of t plus b sub 0 u of t. And if I wanted an output equation, can I write y in terms of x1, x2, x3, and u? There's really no summing even involved to find y. Y is simply x1 in this representation. The output then equation is y of t is equal to x1 of t. And we can now put this into a state space representation that's called an input feedforward state space representation. And where did that name come from? Do you see that the input is being fed forward to create this state space? It's not just coming in at the left one time, it's actually being fed forward into several summing junctions. So this is now an input feed forward state space representation, which, writing it in a state space form, we have an x1 prime, an x2 prime, an x3 prime equaling, how big is my system matrix A? What are its dimensions? It has to be square, right? And it's 3 tall, it has to be 3 wide. How big is what are the dimensions on my input matrix B? How tall is it? It has to be compatible with the left-hand side, and the left-hand side matrix is 3 tall, and it's 1 wide. And we now simply populate this with the coefficients from those 3 coupled differential equations. We had a minus a sub 2, 1, 0, a minus a sub 1, 0, 1, a minus a sub 0, no more x's, and we had a b sub 2, a b sub 1, and a b sub 0. And here is our input matrix. What's our output matrix, or our output equation? Y of t, we just have 1, so the output matrix is 1 tall. It has to be 3 wide. It has to be compatible with the state vector. We have an output matrix that's 1, 0, 0. We have a direct feed-through matrix. That's 0. And what I would like you to keep in mind with this state space representation, now that we've derived it, look at how the A's structurally populate the A matrix, and the B's, how they go into the input matrix. And what were the B's? The B's were the numerator coefficients in our original transfer function. There's a B2, B1, B0. Our transfer function initially, wherever that was right here. If I now gave you this transfer function, you could say, oh, a state space representation would be an input feed forward, and boom, you just write down by inspection the state space representation, because you know where the B's are, you know where the A's are, you know you have 1s on the super diagonal in the system matrix, and your output matrix is simply 1, 0, 0. So that now if I gave you something different, which I gave you to beginning, I think, the class, I said, here's g of s, and now I had a 4s plus 6 over s cubed plus 7s plus 12. And in this particular representation, do you see that we had a 0s squared and we had a plus 0s squared down below? And where are the B's and the A's? Here's B2, B1, B0. That one was monic. That would have been like an A3, but we normalized that to be 1. Here's our A2. Here is our A1. And here is our A0. Do you see how we would populate these now in a state space representation? We just negate the A's and put those in the first column with 1s on the super diagonal. The B's go from B2 down to B0 in the input matrix, and the output matrix is 1, 0. That we can do AC after class. So look for after class, and what I will probably do after class is also include how you would change this up if I now gave you a transfer function that had a numerator that was the same order as the denominator. This assumes a strictly proper to find the A's and the B's. We'll pick up maybe with a different strategy next time.